Okay, so let's take a look at question number 12 from the electrostatics test. It says, a small charged plastic ball is vertically above another charged small ball in a frictionless test tube as shown. The balls are in equilibrium, a distance d apart. If the charge on each ball is doubled, the equilibrium distance between the balls in the test tube would become what? Okay, so they give us a picture. Two spheres, they have charge on them. We don't know the charge, but we know that they're distance d apart. If they're at equilibrium, we do know something. We know that this ball feels equal and opposite forces. So gravity is pulling it down, Fg, and that means whatever this electrostatic force is between these two spheres must be repelling it up. So I'll call that F little e for our electrostatic force. So now we double the charge in each one of these spheres. If this sphere has a double the charge, and this has double the charge, where do we expect them? Are they going to get closer together? No, they're repelling, and then they're going to be repelling more. So later on, set up the same thing. This ball is still at the bottom of the test tube, but this other sphere will be higher, and it's going to be some different distance. Now let's think about this. At this distance, has gravity changed on that top sphere? No. It still feels Fg, which means we're looking for the distance away, this distance, where the force will still be equal to Fg. So over here, we said Fg equals Fe. So that Fg is a constant. It's some number. We don't know what it is. But Fe is K. And we'll call this, let's call the bottom sphere 1 and the top 2. And we'll call this 1 and 2 over here. So this is Q1, Q2 over. And this is our distance squared. And now, these charges are going to be doubled. Okay? So a nice little trick is that we can play the ones game. We could just say that 1 equals 1 times 1 times 1. We plug in 1s for K, Q1, and Q2, and our distance squared. And then over here in our second scenario, we still have the same equation. We say Fg equals Fe. And that Fg on this side, we're saying it's still equal to 1. Q1, Q2 over something squared. And this is still 1. Fg is still 1. Why is it still 1? This is the main part of the problem. You got to realize we haven't changed the mass from situation 1 to situation 2. The mass hasn't changed. So this downward component of force, this force of gravity, is the same in both places. Okay? So that means we're looking for a point somewhere farther away where our electrostatic force is still equal to Fg. It won't be equal here at the distance d anymore. It's going to be a lot stronger at d. So somewhere farther away, it will be equal to Fg. So Fg is equal to 1. Well, K is still the same. But now we've doubled. We've doubled Q1. So no longer is it a 1. It's now double of 1, so that's 2. And this one, Q2, is no longer 1. We've doubled it, right? That's what the problem tells us. We've doubled those two charges. Then we say, well, what is that distance? Well, hopefully, now that we realize that that electrostatic force, we want it to still equal that Fg, which hasn't changed, we see that this ends up being a 4 in our numerator. And we want something squared so that this fraction turns into 1. And we can see that that distance is now 2. So if on the left side we had a distance of d, now we have a distance of 2D. And there we go.